So this is the second of two videos that I'm doing to help you prepare for the take-home test on ASCII, ANSI, and binary and how they're related. So in the first video I talked about ANSI and ASCII, ANSI being the American National Standards Institute, which brings together people, companies in different industries to come up with standards which in the long run is better for us as consumers and customers, so that no company can more or less monopolize and run everybody else out of business. So the ANSI Standards Board got the big players in computing history back when computers were first becoming popular to agree that they would translate letters, numbers, and symbols on the keyboard to specific numeric values so that they could then be stored on the computer. So that brings us to the concept of binary. So as I know I've said many times, and you're probably tired of hearing, if you could open up your laptop or computer, or even your flash drive, and if you could actually look at back in the day it used to be a magnetic disc, a round circle with tracks on it similar to a small LP record or vinyl record. Those tracks would have data. They've kind of changed the inner workings of the hard drives. But the bottom line is, whether it's a flash drive or a hard drive, if you could actually look at what is written to and stored on the hard drive, if you had a magnifying glass that was powerful enough that you could see the tiny pieces of information that were written or stored to the hard drive or to your flash drive, you would never see words on there. Even though you might have Word documents on there with sentences and paragraphs, that's not what you'd see. You would see only numbers stored on the hard drive. And in fact, they would not be the numbers you're used to, which are decimal numbers. Decimal is base 10, which is why we have the numbers 0 through 9. That's 10 digits. And then we have ones, tens, hundreds, thousands, all powers of 10 representing our decimal numbers. Well, we translate the various characters, letters, numbers on the keyboard into a decimal number, and I think maybe 32 is a space, and I can't remember, I'd have to pull up an ASCII chart, but 35 might be the capital letter A, I can't remember. But when you're typing your Word document, it's a convenience for you, for usability, that the software lets you type the letter A and displays the letter A on the page. It lets you hit the space bar and there's just a space there. But behind the scenes, what Word or any other software is doing is it's translating those values into numbers, because the computer understands numbers. It doesn't understand anything else. The software that we write helps the computer understand or translate and then redisplay words, say in a word processing document. The software on the computer, the operating system, the compiler, the Visual Studio integrated development environment that we'll be using, all of that works together to help the computer understand the meaning of what you're typing in. But ultimately what gets stored to the hard drive and saved so that you can pull it up later is only numbers. And those numbers, if you remember, you can look at the ASCII chart. So every manufacturer, every big player in the computing industry, everybody uses this ASCII code. Whether it's Microsoft or Google, doesn't matter. They're going to use the same code to translate letters, numbers, and symbols so that they can be stored as numbers on the hard drive, because computers work better with numbers. And my computer's a little slow here, but if the ASCII table comes up, we will see that when we type certain letters, numbers, symbols, they get translated to some decimal number. So we're only concerned about the decimal column and the character column. You can ignore the hex and the octal columns. We're not dealing with those. Those are entirely different numbering systems for different uses. So if I wanted to look at the decimal character 32, that's a space. So when I type the space in Word behind the scenes, it translates that to the number 32. If I wanted to type an H, a capital H, it would translate that to a 72. If I typed an E, it would translate that to this number. If I wanted to do two L's, it would do 76, 76, and then O would be 79. And if I hit the space bar again, it would put a 32. Now, it's easier for us because we are trained in decimal, that's our numbering system, to look at a 32 and say, oh, that's a space based on this ASCII chart. What gets written to the hard drive, if you had that powerful magnifying glass, would not be the numbers 3 and 2 in decimal for 32, but instead the computer really only likes to deal with two numbers, 0 and 1. 0 and 1 kind of being off and on states, almost like electrical circuits are off and on, because a computer is really just an electrical device. So 32 gets turned into the binary equivalent, the base 2 numbering system equivalent, and those zeros and ones are what are written to your hard drive. So if I wanted to say, put the number, if I wanted to hit the space bar, it's going to translate it to a 32. And then using one of the Khan Academy videos, in particular the one where the guy just basically wrote the powers of 2 on one hand, on the fingers of one hand, you could figure out how to write 32 in binary, because all binary is a numbering system based on 2 raised to different powers. So 2 to the 0 power is 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, 2 to the fourth power is 16. So if I wanted to translate 32 into binary, I could take the powers of 2, draw my hand diagram like they did, and then figure out anywhere. I'm going to take my powers of 2 and add them up until I get 32, and the way I designate which power of 2 I'm using is under that column. If you watch the one where he did the hand, you put a 1. If you're not using that value, you put a 0. An easier one to convert off the top of my head is the number 2. So if I wanted to turn the number 2 into binary, so my first position is 2 to the 0 power, which is 1. My second position is 2 to the first power, which is 2. So I would put a 1 in my second column saying I want 1, 2 to the first power, that's 2, and then I would put a 0 behind it saying I don't need any of the 2 to the 0 units. Now you can represent the number 2 as 1, 0, or some people will pad that out to an 8-bit character string, so they'll put 6 zeros in front, 0, 0, 0, 0, 0, 1, 0. And the reason they do that is because each 1 and each 0 on the hard drive is considered a bit. A 1 is a bit, a 0 is a bit. That's the smallest unit that you can write to the hard drive, either a 1 or a 0. They're both bits. When the computer wants to start translating things, it wants to work with 8-bit units. So it really wants to deal with numbers that are in 8-bit representations. So that's why you'll see some people put 6 zeros and then 1 0, because that's 8 characters or 8 bits, which is a byte. That's a unit that the computer likes to use. So I don't care if you put 1 0 or 0 0 0 0 0 0 1 0. To me, either one of those is the representation of the number 2 in binary. And then the other thing is with the ASCII code, we have a total in the very, very basic ANSI standard ASCII table of 127 different letters, numbers, characters that we can represent. Things from when you hit the return key, forcing the carriage return to the next line, symbols. Remember I said in my last video the number 9 isn't represented by the number 9 in decimal or binary, it's 57. So translate 57 to binary, that would print out or show up in Word as the number 9. There is an extended ASCII table that the ANSI folks agreed on, so they could do some different characters, and I think there are some for different foreign languages as well, but for our purposes we're just concerned with the first 127 values roughly. And so on the test, I would not ask you to convert a large number like 127 to binary. I'm going to stick to lower numbers, just because if you can do a lower number, you can do a larger number, especially if you just plot out on paper all of the powers of 2. So if you go back and you watch, this particular video is really pretty good on how to do low, small numbers converted from decimal to binary. Here's another one that's got more on binary. The Khan Academy ones are good, and this Virginia Tech interactive exercise is good. So I encourage you particularly to go back and look at this one as relating to a quick and easy way to use your hand, to count on your hand basically, to get your numbers in binary format. So I think I'm going to leave off here with the test review. That's pretty much it. Multiple choice format. You may use your notes, you may use lectures, videos, etc. to take the test. It's going to cover the concepts of ANSI, ASCII, and decimal to binary conversions. If you have any questions, let me know. I'm running a little behind on email, but I'm trying to get caught up on that and grading. And once again, after you take the test, if you want to submit test corrections for half credit back, you will be able to do so. So keep that in mind as an option.